the session chair, the organizers, for a wonderful workshop. I'll talk about quantum coherence due to the system-based interaction. It's also known as the Polaron effects. So I'm involved in this field only in the last 2 or 3 years, quite recent, and I'm also from chemistry. So my talk is going to be more computational than conceptual. Yeah. So I'll introduce the concept of a Polaron transformation using the spin-boson model. Then we discuss heat transfer in non-equilibrium spin-boson model. Finally, I explore the performance of 3-level systems. And here's a brief review of the standard theory for open quantum systems. They are here's a system coupled to the base with the system-base interaction. If this interaction is small, then we treat the interaction as a perturbation. So the result is the Redfield equation. And the rate will increase with the coupling strength and the temperature. At a long time, the system will reach an equilibrium state in the eigenbasis. In the opposite limit, the strong coupling, then we take the part of a system Hamiltonian as a perturbation. The result will be Fermi golden rule rate, or the NEBA. Then the rate will decrease with the temperature. At a long time, it becomes a thermal equilibrium in a local basis. The problem is how to describe the open system in the intermediate range, intermediate coupling. So why are we interested in the intermediate coupling strengths? So I use the example of light harvesting energy transfer. This is a popular system, FMO, photosynthetic antenna complex of green sulfide bacteria, studied by many groups, including Harvard, MIT. So the energy starts from molecule 1 and 6, and then transfer to reaction center through site 3. And to efficiently transfer energy, we want to minimize the time from initial excitation to final trapping. So we calculate the mean first passage time. And here's the result. So the average time as a function of real organization energy. Indeed, at the intermediate coupling strengths, the average time is minimum, and the efficiency will be maximum. And it turns out most light harvesting systems operate in the intermediate system-based coupling strengths and intermediate temperature. So that's the optimal region. That's the reason we are interested in this intermediate coupling. And one cannot treat that with a straightforward perturbation. Instead, we use the Polaron technique. And the Polaron is an old concept. So when a particle moves, a charge moves in a solid, it distorts the lattice and it carries distortion with it. And this quasi-particle is called a Polaron. And we use this idea to treat the strong system-based interaction. So we first start with the spin-boson model, the standard model for quantum dissipation. And here is the spin-boson Hamiltonian. The S is a unitary matrix operator which defines the Polaron transformation. And the B is a displacement operator. So the Polaron transformation is to displace the phonon modes. And after the transformation, we get the transformed Hamiltonian. In this transformed Hamiltonian, the coupling becomes weaker. For example, the off-diagonal tunneling delta becomes kappa delta. And the kappa is the renormalization factor due to the Polaron transformation. They're always smaller than 1. The system-based interaction becomes V tilde, which is also dramatically reduced. So as a result, after Polaron transformation, we can still use the second-order perturbation theory to treat strong system-based interaction. And before we do that, let's look at the thermodynamics. Now, classically, when a system is weakly perturbed by thermal baths, it maintains the Boltzmann function. In quantum mechanics, we take the entire system plus bath Hamiltonian, and we trace out the bath coordinates. The result is a reduced density matrix. Now, because the system Hamiltonian does not commute with our system bath interaction, the reduced Hamiltonian is not the same as the Boltzmann function. And this will add additional quantum corrections to the potential of a main force. Okay. And here's one example. It's a highly biological system called LH2 of a purple bacteria. Now, previously, the Schrodinger's group have propagated the density matrix of the system for a very long time. And they found that the long time limit is not the same as Boltzmann. And of course, this long time limit is the reduced density matrix. So we calculated that, and we found that even at room temperature for this highly chemical system, the difference in population is about 20%. And this is purely due to the quantum correlation. Okay. And this effect we can capture with a Polaron transformation. So this is the system part of a Polaron-Transformed Hamiltonian. As I mentioned earlier, the off-diagonal coupling delta reduces to kappa delta. So as a result, the energy gap will change when the system-bath interaction changes. So here we increase the gamma. Gamma is the system-bath interaction strength, or the friction. As we increase the gamma, the kappa becomes smaller. As a result, the energy gap in the two-level systems becomes smaller. So the population difference also becomes smaller. And in addition to the population difference, the eigenbases will also rotate. So the pure system, the system Hamiltonian define an eigenstate, which is a vector here. But the reduced density matrix will define another basis set, which is this vector. And there's a deviation between these two vectors on the Bloch sphere. And here we plot this deviation angle as a function over coupling strengths. So clearly, as we increase the coupling with our baths, there's a rotation from eigenbasis to the molecular local basis. And this rotation is also captured by the Polaron transformation. It comes out automatically from this Polaron transformation. Finally, we turn to dynamics. As we mentioned earlier, in a reduced frame, the system-bath coupling becomes weaker. Therefore, we can still use the second-order Redfield equation to treat strong couplings. And here's the Polaron-Transformed mass equation, the Redfield equation. It's very similar to standard Bloch Redfield equation, but the rates become much more complex. This is expression for the rates, and this is renormalized by the Polaron transformation. So all the quantities here are no longer defined in the initial basis. It's now defined in the Polaron basis. I mentioned two things. First of all, this equation, when the coupling is weak, this equation becomes identical to the Redfield equation in a weak coupling. In a strong coupling, the coherence will be suppressed, and this equation will give us the Fermi golden rule rate. So in other words, it gives the two limits correctly. Also, if we propagate this equation for a long time, it gives us the thermal equilibrium, which is identical to the this Boltzmann factor in a reduced Polaron frame. In other words, this equation is thermodynamically consistent. Yeah. At a long time, it goes to the right thermal equilibrium. So far, we introduced the Polaron transformation. And now we can use this technique to calculate two-level systems, three-level systems. So I started with a heat transfer in a non-equilibrium spin-boson model. And first, we calculate heat current. Then we calculate the fluctuations of the heat current. And finally, we try to improve the Polaron method. Heat transfer, of course, is an important part of the thermodynamics. And the non-equilibrium spin-boson model is the simplest model for quantum heat transfer. So essentially, we still have the two-level system, but coupled to a hot bath, and a cold bath. The model has been studied extensively by many groups, including David Scovil here. When the coupling is small, the heat transfer is essentially a single photon process. And heat current can be given by the Redfield rates. When the coupling is strong, the heat current is given by Fermi golden rule rate, also known as the NESB rate. What about the intermediate coupling? Well, numerically, we can calculate the current for this intermediate range. But theoretically, we don't have a closed form expression for the heat current. And now we can combine the Polaron transformation with counting statistics. As a result, we'll have expression for the heat current. And again, this expression, all the quantities are defined, are renormalized by the Polaron transformation. For example, the Q is a correlation function of the bath in an original basis. But after transformation, the correlation function will involve coach of the Q, which is a product of many correlation functions. And again, this complex expression also have nice limits. As mentioned earlier, when the coupling weak, we'll have a Redfield heat flux. And indeed, this expression reduces to the Redfield expression. When the coupling is strong, it reduces to the NESB rate, which is also known as a Fermi golden rule flux. Yeah? And now we can use this expression to calculate heat flux for the intermediate coupling strengths. And here's the result. For comparison, we also show the Redfield flux, which is a dashed line, and the NESB flux, which is this curve. So clearly, the Polaron solution goes in between strong and weak coupling limits. It also predicts a maximum heat flux at the intermediate coupling strength. And alpha is a system-based interaction strength. When alpha equal to 1, the heat flux is the maximum. In other words, the optimal heat transfer occurs beyond the perturbative region. It is non-perturbative. It's in the intermediate coupling strengths. We also show the coherence, the off-diagonal sigma x. And at a maximum heat flux, the coherence changes dramatically from constant plateau to 0. So the coherence is associated with a peak, the maximum of the heat transfer. Further, we can calculate the heat flux as a function of temperature of the hot bath and temperature of cold bath. And this result shows that our solution applies not only to small temperature difference, but also to large temperature difference, which is beyond linear response. Okay. So we discussed the average heat current, But in addition to the average, the heat transfer is a stochastic process. It also has fluctuations. So how do we calculate fluctuations of the heat flux? So standard definition of heat current is the amount of heat, transferred heat, normalized by time. The fluctuation is defined as the variance of transferred heat over the divided by time. So according to the Onsager linear relation, the fluctuation is proportional to the thermal conductance. So to verify this, we should really derive expression for the J2, the second cumulants, the fluctuations of heat. And indeed, we can obtain expression, it's again the Polaron expression for the J2. And other quantities here are given in the Polaron frame. We'll not go to details, but let me calculate this quantity, calculate this expression. And here is the fluctuation of the heat as a function of alpha. Alpha is a system-based coupling strength. The dots are the solution. The solid curve are the thermal conductance. And indeed, they agree perfectly. And this is their prediction of the Onsager relation. The fluctuation is proportional to thermal conductance. But on the right, we increase the temperature difference. So the no longer in the linear response region, there's a larger temperature bias. So the linear response will fail. As a result, this is a thermal conductance, and it differs from the fluctuations. However, there's a second curve, the solid curve, which agrees perfectly with the fluctuation. And the solid curve is a generalized version of the Onsager relation. So let me explain where does this generalized version come from. It comes from the fluctuation theory. Yeah, because of time reversibility, the cumulant Jianshu function has a nice symmetry relation. And here chi is a counting field, A is affinity. So then we take derivatives of the counting field and the affinity. We're able to find a set of identities. So there's an infinite number of such identities. The lowest order identity is exactly this generalized Onsager relation. So this identity applies not only to small temperature difference, but also to large temperature difference. And if we take the linear expansion, it recovers the Onsager relation. So essentially, this identity comes from the fluctuation theory of the heat. And in this paper, we show that the Polaron-Transformed heat expression follows the fluctuation theory. Therefore, it's not surprising it recovers the generalized Onsager relation. In fact, it also will create cumulants which are based these identities. Okay. So now we have discussed the average heat current and the fluctuations around the average. The next question is how reliable is the Polaron transformation? For this, we can compare with the exact numerical calculation. And this is the same plot, the heat flux as a function of coupling strengths. The upper curve is the Polaron solution of the heat current. The lower curve is a numerical solution, is an exact, numerically exact solution. So it has the same shape, but there's some small differences. Quantitatively, they have difference. In addition, the Polaron transformation has a much more severe problem. The problem is that when we deal with an ohmic or subohmic spectrum, thermal bath, there's infrared divergence. In other words, in a definition of the renormalization constant, the exponent will be infinite. So as a result, the kappa will be 0. This will kill all the coherence. So there'll be no coherence left. It's only going to be incoherent Harbin if we use Polaron transformation. That's the problem of infrared divergence. The other way to understand this problem is that the Polaron transformation enforces the phonon mode to follow the dynamics of a system. And this works perfectly if the phonon frequency is large. But for low frequency mode, it is too slow to follow the motion of a system. And it's almost frozen. Therefore, one cannot apply the Polaron transformation. To solve this problem, we introduce a variational Polaron technique so that not all the modes are displaced. Only the high-frequency phonon modes are displaced. The low-frequency modes are frozen. And the percentage of their displacement is given by this variational parameter, f omega. We can now determine this function from the variational calculation. And this is done by my former colleague, Bob Silby, and his coworkers. So when you use a free energy bound to optimize the displacement, then one can find a self-consistent equation for this variational function. And this works very well for the spin-boson model, even at the 0 temperature. Yeah. But the problem is how can we extend this to heat transfer? Because heat transfer involves not only one bath, but two baths at different temperatures. What temperature we use here is the two different temperatures. And in order to apply this variational method, we have to define a partition function for the non-equilibrium steady state. How do we do that? It turns out there's a formal solution in literature. It's given by, this almost looks like Boltzmann factor, but it is for non-equilibrium system. And it involves this operator called Y operator. So this is also known as the Y operator formalism. It's difficult to actually evaluate this Y operator, but this actually is a good starting point to construct an approximate partition function for heat transfer. And that's what we did. So inspired by this definition of a non-equilibrium steady state, we take the partition function as a product of three pieces: the cold bath, hot bath, and the effective temperature for the system. Then we use this as a variational bound and optimize the Polaron displacement. And this is a self-consistent solution. Now this solution is no longer local in terms of a bath. In other words, the displacement of the phonon modes in a cold bath is actually depend on hot bath. It's not local in terms of a system-bath interaction. So this technique applies to a non-equilibrium spin-boson model, but it can also be extended to three baths or a network of heat baths. So now with this variational method, we can again calculate heat transfer and see how it works. So now this green curve is a numerically exact solution, and the up curve is a standard Polaron solution. The black curve is the variational Polaron solution. So clearly, the agreement with the exact solution is dramatically improved. We can also go further to calculate the heat transfer for ohmic spectrum. So the standard Polaron transformation will diverge. But now, with the variational Polaron, we can get very good agreement with the numerically exact solution. This is a non-equilibrium Green function calculation. And again, it agrees perfectly. Yeah. For reference, we also plot the Redfield solution and the Niebuhr result. So our solution goes in between these two limits. Okay. So this is a discussion about two baths, heat transfer. But now we move to three baths. And now we discuss their performance over three-level systems. We deal with two examples. One is a three-level system for three-level model for light harvesting energy transfer. The second is the three-level heat engine. So you know, photosynthesis converts sunlight, solar energy, into chemical energy, whereas the heat engine converts heat into work. And so as shown by Scovil, there's a close relation between these two processes. And inspired by this paper, we decided to study the first step of photosynthesis. That's light harvesting energy transfer. So here's a basic process, the basic steps. The sunlight is absorbed by pigments to create excitation, excitons. The exciton will hop in a pigment protein environment and eventually will be trapped at the reaction center for charge separation. This is the initial step of photosynthesis. So the basic step can be described by simple three-level system. This is the ground state and then two excite states. In the three-level system, there's three transitions, and each transition is coupled to different phonon baths. So the first bath is the excitation due to the sunlight. It's incoherent excitation. The second bath is the trapping at the reaction center. And this is preparation for the subsequent steps. The third bath is the coupling to the dissipative bath of the protein environment. And the quantum efficiency is the ratio of the energy flux to the reaction center over the energy flux from the sunlight. So this is the efficiency. So clearly the three-level system is a popular setup. And a more famous, a more well-known example is the three-level laser, maser. And it's been shown decades ago that efficiency is given by the ratio of two transition frequencies. And it's bounded thermodynamically by the Carrot efficiency. Okay? And this is based on the weak coupling limit. I'll discuss this later. Our model, instead of a driven mode here, we couple the 1 and the 2 states with another thermal bath. So the 3 heat bath model. In a strong coupling, we can ignore quantum coherence. Then the energy flux is simply the population flux times the transition energy. So the result, the population flux is conserved in the loop. So the result, efficiency is simply the ratio of two transition energy. This is the same result established decades ago. Okay? But it is for this 3 heat bath problem. But the assumption involved, the assumption is that the coherence is 0. And it's certainly not true if we have weak damping. Okay. To account for coherence, we have to write down the quantum mass equation for this 3-level system. And it involves 3 dissipative terms. The first term is the excitation from the sunlight. The second term is a trapping at the reaction center. And these 2 couplings are weak, so we use the Redfield-Bloch operator. The last term is coupling to the protein environment, and that interaction is not necessarily weak. So we use the Polaron-Transformed Redfield equation. We can also define the heat flux, or the energy flux. It has three terms. The first two terms are exactly the population transfer. The last term is associated with a coherence. So if we ignore this last term, we go back to the classical limit. Efficiency is a ratio of transition frequency. But now, due to this coherence, there's corrections to this result. And how does this work? So we calculate this, and here we plot the efficiency, which is a red curve, and the energy flux, the blue curve, as a function over gamma. Gamma is friction, which is the system-based interaction strength. So as expected, when the coupling is very strong, we kill all the coherence. And then we recover the classical SSD efficiency. But the power or the energy flux is extremely small. So to enhance the energy flux, we have to reduce the system-based coupling strength. Then it will reach the maximum at the intermediate coupling strength. So this is my optimal performance. That's a maximum heat flux, energy flux. And this will be the efficiency at the maximum power. So that occurs at the intermediate coupling strength. And this is also consistent with what discussed yesterday afternoon about the optimal performance at the intermediate coupling strength. Also, we show the steady-state density matrix of the up two levels. And you can clearly see at the optimal region, the population is highly inverted. So that's a maximum inverted population. And the coherence changes dramatically. So similar as a heat transfer, the performance